I'm Yanni Chen.
I'm Graham Pence.
I'm Tyler Dennis.
I'm Ben Rashid.
Today we'll be talking about force feedback joysticks. More specifically, we'll be talking about what force feedback is, the basic idea behind force feedback systems, the vibration motor of a force feedback system, DirectX, and also programming of the force feedback system. So what force feedback is, it's a type of haptic, and a haptic gives a user touch feeling instead of auditory and visual feedback through speakers and a monitor. We use force feedback when we want a user to control the joystick in conjunction with an on-screen action. So where do we use force feedback systems? Well, force feedback systems are used in a number of computer games and also programs. They're especially used in flight simulations because it helps a pilot feel that the force feedback joystick is working and also stimulates actual flying conditions. It is also used in racing games, and you can feel it when your car hits a wall. Force feedback is programmed into a software by a team of software developers, and it can be specific enough to one particular brand or type of joystick, or it can be generic enough that it works on a wide variety of joysticks. The advantages of a force feedback system is that it adds realism in a situation, so then when the user is using the force feedback system, it has an output from the system. So it gives a perception that the user has the control of the machine that they're working on. A disadvantage of a force feedback system is that it requires external power because the power supply to the USB is not great enough, and it is also more expensive than a joystick without force feedback. The four types of sensors that are used in a force feedback system are variable resistors, magnetic sensors, which also include Hall sensors or magnetoresistors, optical sensors, and tensometric sensors. Our force feedback joysticks that we use in our 480 project, it has two variable resistors, or two potentiometers, which measures the x-axis and the y-axis, and it also uses an optical sensor. Our joystick that we use in 480, it has the optical sensor, and it's actually a hand sensor which detects the presence of a hand on a joystick. And it has an infrared light and also receiver. So when your hand wraps around the joystick, the infrared light is covered up. And when the infrared light is covered up, then the force feedback power section is activated. But when there's not a hand on the joystick, then there's no force feedback activated. So next, Graham will talk about the force feedback joystick, the idea behind it.
So yeah, I'm talking about the force feedback structure and how it relates to voting. So unlike normal joysticks, it has a couple of components here. One being the microprocessor. This is where we can modify how much force we want precisely, for different positions of the ballot. And then the processor connects through electrical signals to the position sensor, which controls the motor and how much force it needs to be activated to the joystick. Being that there's two motors, one for the X and one for the Y axis. Commonly, they're also called actuators, which can range, in ability from being able to have a certain amount of impedance or having full range of position. So this is a big picture of our joystick in the making here. It has some of the similar components. It has the two motors, and we made some design modifications to it as well. We decided to go with the golf ball. It gives the user stability when you're trying to change selection through voting. We also made this whole exterior right here. And we decided to go with a steel case. This is going to add some weight to the joystick, so it keep it in place, so it doesn't move around as much, and it should give more strength for any wear and tear usage. So this overall circuit for the motor circuit, this is going to be able to control how the joystick moves from left to right. So it has a left drive and a right drive. Most of these consist of a 24-volt source connected with four transistors on each side with four MOSFETs in the middle, which connects to a H-bridge here. This H-bridge is going to is the main way that the connections work between moving from X and Y axis. And I'll talk more about that. So what's good about the H-bridge is the voltage runs bidirectional, so it's really good for objects that need to have force in both positive X direction and negative X direction, which is great for a joystick. So for example, if I wanted to move the joystick to the right, I would activate the switches S1 and S4, and open S2 and S3. So this will cause a positive voltage in the right direction. If I wanted to have voltage in the opposite direction, I would do the opposite. I would close S2 and S3 and open S1 and S4. So basically, if I wanted to go in the forward right direction, I would have to activate two H bridges, because there's going to be two circuits going on at once. And they're both going to be activating S1 and S4 for this action to occur. Besides that, you can also go do other things. You can break the motor. Normally it runs at 0, 0, 0, but when you want to break it, you're either going to want to close S1, S2, or S3, S4. And those are some of the main stages, but basically, for the most part, you just use the two basic moving right and left. So we decided to make some force modifications to our joystick. We have an external knob on the outside of our joystick, which the user can basically change the amount of force they want for each section of the ballot. Some parts might have more selections, you want to add the amount of force so it doesn't go all over the place. We measure it at 17.4 kiloohms. This amount of resistance should be enough to keep the current down, and it should work well for our circuit. So yeah, it should definitely help for any users, trying to make different changes of different ability. So we had someone come into Stephen Blosser's office. It's a friend of his. He's got cerebral palsy. We had to block out his face for privacy issues, but he helped us test our joystick to make sure it works, and how it worked with the Georgia Tech voting software, and how the force feedback issues affect him and whatnot. And it seemed like he gave him good control. He was able to go through the different selections. The one issue we had was he was actually stronger than we expected, so the joystick occasionally would actually slide from the table. So we definitely had to make sure it's mounted in the future use of voting.
I'm going to talk about the motors we use for this project. One possible way to achieve force feedback is using vibration motors to create a vibrating alarm. Vibration motors is a compact-sized cordless DC motor that we use to inform a user of receiving a signal by vibration instead of sound. The vibration motors are widely used in a variety of applications, including cell phones, GPS, pages, and so on. The main feature of the vibration motor is the magnet-conus DC motor are permanent, which means it will always have its magnetic properties. This is compared to the electromagnet. Another main feature is the size of vibration motor are small and the weight are light. What's more, the noise and the power consumption the motor produce while using it are low. Based on these features, the performance of the motor is highly reliable. The vibration motors are configured in two basic varieties. The first one is coins, and the second is cylinders. The cylinder type is also called bar type vibration motor, and here's a picture of the bar type vibration motor. As you can see, this kind of motor is essentially a motor that is improperly balanced. This means there is an off-center weight attached to the motor's rotational shaft, and it will produce a centrifugal force while rotating it. This unbalanced force will displace the motor, and the high-speed displacement will make the motor to womble, and which is known as the vibrating. And this womble can be changed by the weight mass attached to the shaft, and the distance between the weight and the shaft, and also the rotating speed of the motor. And this centrifugal force can be calculated by the equations shown on the screen. In summary, a larger weight mass with a bigger offset from the shaft will produce more force and hence more vibration amplitude. Also, decreasing the power supply to the motor also increases rotating speed, so that the vibration frequency and vibration amplitude will increase as well. The need for smaller, thinner design led to the adaptation of brush motor technologies into the coin-type vibration motor. As you can see from the picture, this type of motor contains a weight, a ring magnet, A rotor with commutation points assembled in the front and coils assembled on the back, and also power supply brushes. The commutation points, which are the yellow part on the screen, are also connected to the end of the brushes. It will energize the electrical coils in the rotor. Energizing the coils will produce a magnetic field, and it is strong enough to interact with the ring magnet integrated into the stator causing rotation. Also, a force is also generated due to the magnetic field, and this force will displace the weight as well. The repeated displacement of the weight will creating a varying force that will make us feel like it's vibrating. Also, the commutation points are used in changing the polarity pairs so that as the rotor moves, the coils will constantly reverse the polarity.
All right, I'm going to talk a little bit about the software side of programming force feedback joysticks. So Microsoft a while back decided to create a protocol called DirectX. The point of DirectX is to kind of streamline the application development process for people who want to develop multimedia applications on their operating system. What DirectX is, it's a collection of APIs, or application programming interfaces. What an API is it's a library of classes, data structures, and routines. These libraries can be used as headers in high-level programs in order to bypass the need for any low-level programming to interact with hardware directly. So an example of one of these APIs is called Direct3D. Direct3D is actually used to create 3D graphics engines. And what it does, it includes a bunch of classes and data structures that you can call instead of having to do like low-level assembly programming in order to communicate with the video card in a computer. You can just communicate indirectly on a high level, which makes things a lot less complicated for the developer. These APIs are included in the DirectX SDK, or Software Development Kit, which you can download for free off Microsoft's website. And so an example of a use of DirectX is in video games. This is probably the most common use. So you can use something like Direct3D to create a 3D graphics engine for a game that you're developing. The API that we're most interested in is called Direct Input. It includes classes that are very useful for interfacing input devices such as mice, keyboard, and joysticks with the computer. And the great thing about DirectX for us is these libraries are compatible with C++ and Visual Basic, which are the two languages that we will be mostly working with. Like I said, Direct Input is used for retrieving data from input devices, which works well for us. A great thing is it supports force feedback. So you're able to assign several different aspects of force feedback to a force feedback joystick through high-level programming with C++ or Visual Basic. An example of one thing you can do is you can create a constant force and assign a magnitude to the force. So basically, you can use the magnitude function to increase or decrease the significance of the constant force that you create. Another important one is gain. So sometimes you want to use two different pieces of hardware, like two different joysticks with one specific program. But you can have issues when one piece of hardware, say for instance, has more powerful motors in it than another. The force feedback is not going to feel the same. So what you can do is you can actually adjust the gain in order to scale the force between the two joysticks so that you can get an equivalent feeling for both. You can also assign different force patterns. It's not limited to a constant pattern. There's actually ramping, periodic, and condition, just to say a few. Condition is probably the only kind of ambiguous one up here, so I'll explain it. Basically, a condition force is a force in reaction to a movement of the joystick. So say, for instance, you move the joystick to the left. The condition force you can set to say, okay, when the joystick is moved to the left, apply a force in whatever direction, at whatever magnitude you choose. And here's a couple examples of force feedback patterns. Both of them are actually periodic forces. So say for instance you assign a sawtooth pattern force in the x-axis of a joystick, and we call it negative force to the left and a positive force to the right. In this instance, the joystick will begin with a strong force to the left that will gradually diminish until there's no force at all, and then it will gradually increase. There will gradually be an increasing force to the right, and then it repeats periodically. You can also assign an envelope to these periodic forces. So basically, if you want a periodic force to diminish over time, you can use an envelope that gets narrower over time, like the one seen up there.
Thank you, Tyler. I'm going to talk more about the software design of this project, basically for force feedback. First, we need to initialize the direct input library, as Tyler talked about a little bit ago. First, we have the header files for X different functions that we want. And then, as you can see, we have direct input library and direct X guide library that we're going to use to call different functions. So we're not going to go into low-level programming of this force feedback. We're going to use direct input a create function to send parameters into it, so we can basically initialize the direct input. Next step is to configure the joystick for force feedback. Actually, as you can see, we have a for loop saying that for every device instance that we have inside our enum device method, this is a method that we can iterate through to go through all the devices available to us as an input device, and then get the force feedback attribute of it and assign that device to our joystick and then break out. And then in the case if the joystick is not filled with any of those attributes or any of the devices that we wanted, we're going to throw an exception. Basically, it's a threat that helps us prevent the program from terminating, and this we're going to let the user know that no joystick that supports force feedback has been found. And after that, we need to create an array of axes with force feedback. Basically, it's an integer array that let us work with different directions and give different directions, different type of effects that we want, that I'm going to talk about in a little bit. Now I'm going to talk about assigning effect aspect of this programming, of this force feedback. First, we need to relay a physical constant force on axis of the joystick. First, we need to check if it supports these effects, and then create the effects, set the parameters, and then finally apply them to the axis that you want. As you can see on top of this code, it might be a little bit hard for the folks back in the room, but we're going to use this class called effect, which is in the DirectX library. We're going to make a member variable of that effect called E, and then call different functions with this member variable. As you can see, we're going to make a new effect, and then I'm going to call different two functions, set direction and set axis, and I'm going to send the array, the integer array that I talked about in the previous slide, into them to initialize it. And then the very important part that I magnified it below here is E.effect type, and we're going to set the effect type to be constant force. In this particular project, we're going to use the constant force. We have different kind of effect types that I'm going to talk about in a little bit next slide, but for this particular project, we use constant force. We're going to set the effect type, which is member variable in class effect, to be constant force. And then the duration of this effect will be infinite, because we don't need to have any interrupt for our effect, basically, to make the user confused, whatever. And then we have gain to be 10,000. Actually, Tyler talked about the gain a few minutes ago. We set it to be 10,000, and the rest is going to be the triggering buttons of the force feedback. And then again, we have the exception again. As I talked about previous slide, we need to let the user know if the variable that we wanted is not filled up with any attributes. So we're going to say that constant force is not supported if basically it's empty. So there are different effects of the force feedback that we went through, and then the first one is rumble effect, the very basic effect, and it's been used on game pads and for vibration. Basically, when you're like playing video games, let's say racing, or let's say racing, when you hit the wall, it's going to vibrate game pad. Next one is periodic effect. It repeats itself at some frequency. We're going to give it some offset in magnitude, basically. Third one is constant effect, which we chose for our project. We're gonna give some constant force in a specific direction that we want. Next one is damper effect, slows down the movement in a particular direction. And the last one is spring effect. The more we move the joystick to one direction, the further we move it away to one direction, it's gonna come back to the center with stronger force, which we're gonna actually use that for our project. But the main point is that we use constant force for our project.
All right, here's an example of software that was developed using DirectX libraries. It's called FF Shifter. It's developed by a gentleman named Andres Panos. It's freeware. You can download it for free online. Basically, what he wanted to do is create software that would allow him to easily simulate shifter for a manual transmission on a car. And so basically, you can just draw in forces. You can use constant forces and spring forces, draw them in boxes, and then assign magnitudes and directions to these forces. This has actually been really helpful to us because it allows us to test the hardware of our force feedback joystick before we finished our own drivers. And so it allowed us to know whether or not we had our hardware was properly built. Yeah, pretty much we just use it for testing. It kind of works. It could kind of work as a final project, but there's not really a lot of flexibility in being able to adjust the force. So we're gonna have to end up writing our own drivers, but it's good in the meantime to make sure our hardware works properly. And that's it. Are there any questions?
Thank you.